Hello, everyone. My name is Megha, and I'm working with Professor Alexander Higa and Professor Daniel Price. Today, I will be talking about Timmy, who dared to drink from the Holy Grail. Yeah. So most galaxies have supermassive black holes at their center, which are surrounded by stars living in the nuclear star cluster. One such star is our friend Timmy, who got too close to the supermassive black hole and encountered a tidal disruption event. So, in a tidal disruption event, the gravitational force of the black hole can overcome the self interaction forces of the star. This can result in two possible outcomes. One is a full tidal disruption event, as shown in this figure, where the star comes close to the black hole and is completely ripped apart. The another possible outcome is a partial tidal disruption event, where a remnant is formed. It can go and live its life. So the distance at which the gravitational force of the black hole can overcome the self-interaction forces of the star is called the tidal radius, which is given here in this formula. We parameterize the strength of the encounter by the ratio of tidal radius to the pericenter distance. So in these slides, whenever I talk about show a higher beta value compared to a lower one, I want you to think that a higher beta means the star got closer to the black hole, hence the interaction was stronger compared to a lower beta value. So it's been theorized that about 10,000 to 100,000 stars in the galactic center of Milky Way have had an encounter with the supermassive black hole at some point. Therefore, it's important to understand the properties of these remnants. To do this, we used two different codes. So one is a stellar evolution code called Kepler, which is maintained by my supervisor, Alexander Higa. And the another one is a three-dimensional smooth particle hydrodynamics code called Phantom, which has been written by my supervisor Daniel Price and his collaborators. So the steps we followed were as follows. So firstly, we generated stellar evolution models in the stellar evolution code Kepler. Then we mapped these models into Phantom and disrupted the stars there. After this, we mapped these models back into the stellar evolution code to understand post-disruption evolution of these remnants. So what kind of models did we use for our simulations? So we used 1, 3, and 10 solar mass models at 3 different stages of their lives. We used zero-age main sequence, where the star has just started burning hydrogen in its core, middle-age main sequence, where the star has burnt about half of the hydrogen in its core, and terminal age main sequence, where it has burnt almost 99% hydrogen in its core. This figure here is the HR diagram, which shows the 3 different models that we used along with the 3 different stages of their lives. So in total, we disrupted 9 models around a supermassive black hole. So what kind of properties did we use in our phantom simulations? So we used the million solar mass black hole, which had no spin. We used general relativistic effects. And for our stars, we used a million smooth particle hydrodynamics particles. So now I will be showing you some simulations that I ran. So this first one is a 1 solar mass model, which comes close to the supermassive black hole and loses about 5% of its mass. As you can see, the beta parameter is a small number, which shows that this is a weak encounter. The next simulation I'm going to show is a stronger encounter, which shows a beta value of 1.49. As you can see, the star comes close to the black hole. It's completely stripped apart. Eventually, we will see that this material starts falling back onto itself. At about 30 hours, we will see some form of remnant, which is formed and left behind to live its life. Yeah, so it's still running. And this model loses 80% of its mass during the tidal disruption event. So let's move on to the results. First, the star can lose a lot of its mass and still survive the encounter, as you would have expected. This figure here shows the mass of the remnant as function of the beta parameter. Again, when the beta parameter here, the higher value means the star gets closer to the black hole, hence it's a stronger encounter, which means more mass loss. The key takeaway I want you to take from this plot is that more evolved stars can survive closer to the black hole compared to the less evolved stars. So let's look at the orange lines here. The dotted orange line shows the 1 solar mass zero-age main sequence model, and the dotted dash line shows the 1 solar mass terminal age main sequence model. As you can see, the terminal age main sequence model can survive closer to the black hole compared to the zero-age main sequence model. The reason for this is that when the star evolves on the main sequence, it becomes more dense in the core and its size also increases, which makes it resistant to the gravitational forces of the black hole for much closer to the black hole itself. So that's what we see here. Number 2, Timmy spins. So In a tidal disruption event, we would expect that the gravitational forces, tidal forces would make the outer layers rotate faster compared to the inside, but that is not what we found in our simulations. This figure here shows a one solar mass 0 main sequence model, and the star gets close to the black hole, and there's formation of these vortices around the pericenter, as you can see here. These vortices result in angular momentum transport from the outer layers to the inside, making the core rotate faster than the outer layers. I should mention that these models have no rotation in the beginning, so whatever effects you are seeing is due to the encounter with the black hole. Number 3, TIMI undergoes composition mixing. So this figure here shows the nitrogen-14 composition for 1, 3, and 10 solar mass models at middle age main sequence for a range of beta parameters. As you move across, the strength of the encounter increases, which means more material is stripped apart, and there is also more mixing taking place, and more material is taken out from the core to the outer layers. As you can see, for a beta value of 2.15 for the 10 solar mass middle age main sequence model. So number 4, stellar evolution. So the main goal of my project was to map these models back into the stellar evolution code and understand the post-disruption evolution. This figure here shows the HR diagram, and this shows the success of our mapping procedure. The orange line shows one solar mass model, which was generated in the stellar evolution code, while the blue line shows the one solar mass model that was generated in the stellar evolution code, then mapped into the three-dimensional smooth particle hydrodynamics code, and then mapped back into the stellar evolution code and evolved. So this blue line doesn't undergo any disruption by the black hole. And as you can see, the mapping procedure is quite successful, as the evolutionary tracks are pretty similar. So using a mapping procedure, we mapped back all of our remnants back into the stellar evolution code, and we found that TIMI has found the elixir of life. So this figure here shows the effective luminosity as function of time for middle age main sequence models. We show 1, 3, and 10 solar mass models for a range of beta parameters. Again, higher beta value means stronger encounters. So the more mass a star loses, the longer it can live on the main sequence, which means it has found the elixir of life. We also wanted to see how different is the evolution of a star compared to a star which never encountered a supermassive black hole. So this figure here shows the HR diagram of 3 solar mass models disrupted at 0 age main sequence, middle age main sequence, and terminal age main sequence for a range of beta values. The solid line shows the evolutionary track of the remnants, and the dashed line shows the evolutionary tracks of remnants of stars that were generated in the stellar evolution code, which were never disrupted in phantom. So basically, the dashed lines are stars which were never disrupted in the stellar evolution in the phantom code, but they have the same mass as our remnants. As you can see here, the 0 age main sequence models evolved similarly to the non-disrupted stars of the same mass, but the middle age main sequence and terminal age main sequence models show difference. The remnants are more luminous compared to stars which never encountered a black hole. This shows that tidal disruption events result in overluminous remnants. So this brings to the conclusion of my talk. We found that TIMI and his friends have found the elixir of life. They have lost a lot of their mass but are still able to survive. The core rotates faster than the outer layers, which is contrary to what we expected. This is due to the formation of vortices, which result in angular momentum transport. We also found that these stars are more luminous compared to stars which never encountered a supermassive black hole. So in conclusion, tidal disruption events result in makeover of the stars. Thank you and have a great day.
Thanks for a great talk. So can you have you checked whether or not this effect of the star having a longer life, does it just come from taking away some of the mass? Like if you just sort of evolve the stellar evolution, take out some of the mass without mapping it into phantom, and then continue to evolve it, what happens? Does it have this? I guess I'm asking, is the main effect the loss of mass, or is there other things happening when it comes to the black hole?
So the main effect is the loss of mass, and then there's also mixing that is taking place in the star, which will also result in different evolution, as I showed in these figures. Yeah.
I think you, on one of your plots, you mentioned that more evolved stars can get closer, but I think you were plotting this in units of the beta parameter, right?
Yeah.
And if I understand correctly, because more evolved stars will have larger radii,
Yeah.
for a given beta parameter, if you fix the value of beta parameter, actually means they're further away. So really, are they actually close in an absolute sense? So when you have a beta parameter that goes up, but the physical radii go up, does it actually mean that really you're talking about the same, roughly the same closeness of approach?
Oh yeah, I looked at the pericenter distances as well. So the more evolved stars can get closer pericenters as well, which is what I was trying to explain.
Okay.
Yeah.
Got it. Thank you.
Yeah.
Thanks, Megha. So since you asked so much question, I'm gonna ask a different one.
Yeah.
So when you're mapping back from Phantom to Kepler, you go from 3D to 1D.
Yep.
And that process involves some loss of information.
Yes,
right?
yes.
How do you work around that?
So there's definitely loss of, especially the composition mixing, because we take the average, and in Phantom we have like million particles, but when I map it into Kepler, I only have like 500 beans. So it's taking an average over the beans, which definitely loses a lot of the mixing effect that is taking place. But yeah, so there's definitely loss of information, but that's the best we could do.